Common perceptions of quantum computing sound like this. Quantum computing. Sure, it might break cryptography in about 10 years, but that gives us plenty of time to prepare. And real, tangible benefits from quantum computers. That sounds promising, but today's systems are still at a very basic experimental stage. They're not ready for practical use yet. So why not wait another decade until we have more qubits and greater stability before diving in? Here's why this perspective could overlook important points. There are two aspects to consider. First, the data confidentiality issue. It's not about what quantum computers do today, but about the impact they will have on the data we encrypt today. And second, quantum application opportunities with current technology. Regarding confidentiality. Right now, we must assume that potential adversaries are already collecting encrypted data, storing it away until quantum hardware advances enough to decrypt it later. This harvest now, decrypt later strategy poses a significant risk to data confidentiality today, specifically for information that needs to remain secure for more than a few years. We're talking about critical assets like financial records, intellectual property, or sensitive communications that could be compromised in the future. This isn't just theoretical, it's why governments are acting swiftly. For instance, the UK and the European Union introduced new regulations in the summer of 2025 to enforce quantum-safe practices within the next years. These developments underscore that quantum threats are a hot topic and require attention immediately, not in some distant future. Then regarding feasible quantum applications with current noisy quantum technology, yes, to break modern cryptography with Shor's and Grover's algorithm, we need to wait another decade or so. The complexity of the Shor algorithm demands a large number of very stable qubits. The algorithm will need to run for hours and days. We're not there yet in terms of hardware size and reliability, absolutely true. However, quantum computing offers much more than just code breaking. There are innovative hybrid approaches that integrate quantum elements into classical systems, making them viable right now. A prime example is quantum machine learning. In QML, you leverage quantum processors only for brief core computations, while handling the time-intensive optimization through traditional classical algorithms. This hybrid model lowers the barriers to entry and allows for practical applications in the next 2 to 3 years. You can already develop and test real use cases on today's small and noisy qubit systems. Consider IBM's current Heron chip, which provides access to 150 qubits through their quantum computing as a service platform. Anyone can start experimenting with it today. You don't need to invest in your own hardware. Access is available as a service. In QML feature map encoding, each feature of your input data is typically mapped to just one qubit. You can build QML models that handle over 100 features. That's already at a scale that's practical or very close to it for real-world problems. Furthermore, the stability of today's noisy qubits is sufficient for these short quantum circuit executions. You might also wonder, why bother with QML when classical machine learning works fine? The key advantage lies in how QML encodes and processes features, offering substantial efficiency improvements over classical methods. This has been rigorously explored and confirmed in various scientific papers, showing potential for breakthroughs in complex data analysis. A real-world illustration came in September 2025 when HSBC announced a notable achievement. They successfully trained an algorithmic trading model for the bond market using QML on IBM's Heron chip. HSBC reported a 34% improvement in prediction accuracy and trade fill probability, translating into better pricing, tighter margins, and more efficient trade execution. If you're interested in the details of how QML can be implemented for such predictions, and how feature mapping works, I recommend checking out video 9 on QML at qubit-lab.ch. In summary, while advanced algorithms like Shor's for cryptography cracking may not be feasible until around 2035, QML and similar hybrid algorithms are delivering value already. Embracing quantum computing means rethinking fundamentals, moving from classical bits to qubits, from standard operations to quantum gates, and harnessing phenomena like entanglement and quantum interference. For certain challenging problems, this paradigm shift can lead to remarkable efficiency gains, partly already in the next few years. You might ask yourself, who is the guy talking here? My name is Daniel Hoog. I hold a master's in particle physics along with a teaching degree in physics. I've also earned an MBA and a PMP certification and spent over 20 years as a project manager in innovation, mergers, and transformations in finance. If you're looking to raise awareness about quantum computing within your management team or among your technical specialists, develop a comprehensive corporate quantum roadmap, or need expert guidance in translating business challenges into quantum solutions, I'm eager to assist. Feel free to reach out to me via qubit-lab.ch.